welcome to another module in this massive open online course. So, today we will start looking at a different type of modulation, that is angle modulation, alright. So, in this lecture we will start looking at, so far we have looked at amplitude modulation, we will now look at a different form of modulation that is termed as angle modulation. Okay. And angle modulation can belong to two types, either it can be either phase modulation. So, angle modulation can either be phase modulation or it can be frequency modulation, or it can be frequency modulation, and we will start looking at both these different kinds of modulation. So, angle modulation can either be of the type phase modulation or frequency modulation. So, first let us start looking at phase modulation. Okay. So, now in phase modulation, obviously as the name implies, so we have phase modulation which can be denoted by PM. So, in phase modulation we have the phase of a carrier. So, phase of carrier is modulated by the message, is modulated or varied by the message signal. So, the phase of the carrier is modulated by the message signal. For instance, let us say your carrier signal is AC cosine 2 pi FCT, this is your unmodulated carrier, correct. So, this is your unmodulated carrier signal. What we are going to do is we are going to modulate the phase of this. So, if I take the phase, that is theta I of t, and if I modulate it as follows, that is, this is the unmodulated phase, that is 2 pi f c t, plus now modulate it using a message signal, that is m t, where m t, remember m t is the message signal. So, this is theta I t, this is the modulated phase. Or this is basically your this is the modulated phase. So, the phase of the modulated message signal is 2 pi f c t plus k p times m t. So, you can see the phase is modulated by the message signal m t. So, therefore, the carrier with its phase modulated by this message signal is given as, now the modulated carrier is given as, or the modulated signal is given as AC cosine theta I t, which is basically AC cosine 2 pi f c t plus k p times m t. So, this is a phase modulated signal. So, this is your phase modulated signal, where the phase of the signal is modulated by the message signal m t. Okay. And what you can see is, because of this message signal where the phase is modulated by the message, what you can see is if the message has a discontinuity, that is, for instance, if the message is a step function, for instance, if the message has a discontinuity, then the phase of the modulated signal experiences a discontinuity. This gives rise to high frequency components. So, what happens, the disadvantage with this is that if there is a discontinuity, or let us say this is your MT, if there is a discontinuity in the message signal, this gives rise to discontinuity, or this gives rise to discontinue in the phase of the continuity in phase of the modulated signal, which leads to, and this leads to high frequency components. This leads to high frequency components in the output. So, what we can see is if you have a signal which is discontinuous, right, if there is a discontinuity in the message signal, which is something like this, if there is a discontinuity in the message signal. So, this is your discontinuity. Okay. If there is a discontinuity in the message signal, that means there is going to be a discontinuity in the phase of the modulated signal, and this discontinuity in the phase of the modulated signal gives rise to high frequency components in the output. Therefore, to avoid this, we use another different form of angle modulation, that is termed as frequency modulation. So, frequency modulation is another kind of angle modulation. So, frequency modulation So, let us now come to frequency modulation. So, let us now come to frequency modulation. In the frequency modulation, the instantaneous frequency of the modulator is carried. So, the instantaneous frequency of carrier is modulated by the message signal. So, in this what we have is the instantaneous frequency is modulated rather than the phase. In phase modulation, the phase of the signal carrier is modulated by the message, which results in phase discontinuities. However, in frequency modulation, the instantaneous frequency is modulated by the message signal, and this can be expressed as follows. So, if FIT is the instantaneous frequency, so the instantaneous frequency equals Fc, that is the steady state frequency, frequency of the unmodulated carrier, plus Kf times Mt. Once again, Mt is the message signal. So, this FIT is the modulated frequency. Modulated frequency, or basically the, now you can think of this as the instantaneous frequency of the modulated signal. So, you can think of a signal carrier wave in which the frequency at every time instant depends on the modulating message signal Mt. Okay. So, therefore, the phase, now remember the phase frequency is the rate of change of phase, therefore, the phase of this is given as theta I t equals 2 pi integral 0 to t f I tau d tau, which is basically 2 pi integral 0 to t f c plus k f m tau d tau, which is equal to 2 pi f c t plus 2 pi integral 0 to t k f, or rather 2 pi k f, since k f is a constant, 0 to t m tau t tau, that is your theta I, that is your theta I t. This is the phase, this is the phase of the frequency modulated signal. The frequency modulated signal or FM signal. Therefore, and now you can see, and therefore, the modulated carrier is given as your S of t is basically AC cosine, well, 2 pi f c t two pi k f integral 0 to t m tau d tau. This is your frequency modulated signal. Okay. So, this is the expression for the FM. So, this is S t is your frequency modulated signal. Okay. So, we are saying that the carrier, the frequency, instantaneous frequency f I t is basically f c plus k f times m t, and therefore, from that, by integrating the frequency from 0 to t, you can get the phase, because the phase is the because frequency is the rate of change of phase, and from the phase you can get basically the modulated carrier, all right, and this gives you the expression of the FM signal. Also, now f I t, remember f I t equals, you are using this relation, we can also get f I t, remember this, it makes sense to remember this relation, f I t in the instantaneous frequency is the rate of change of the instantaneous phase, that is d theta I t divided by d dt, and also we have used basically the relation that, therefore, it follows that theta I t equals, and this has to be there has to be a factor of 1 over 2 pi, and theta I t is basically integral 0 to t f I tau d tau, that is the expression for the instantaneous phase. Okay, that is the expression for the instantaneous phase. And further, one can define the peak frequency deviation of this, the maximum frequency deviation can be defined as, well, maximum frequency deviation can be defined as, this can be defined as maximum of magnitude of f I t minus f c, which is equal to the maximum of magnitude f I t minus f c, you can see that is equal to k f times m t, which is equal to, well, kf times the maximum of magnitude mt, that is your delta f, that is your maximum frequency deviation, or basically the peak frequency deviation. So, this delta f is basically your maximum frequency deviation, or basically it denotes the peak frequency deviation. Okay. This is the meaning, or this is the definition of the quantity delta f. Okay. Now, let us consider a simple example. Let us look at a sinusoidal modulating signal. So, let us consider a specific example of sinusoidal modulation. Let us look at a specific example of sinusoidal modulation. In that, let us once again start with phase modulation, that is PM, and let the modulating message signal be MT. Modulating message signal is MT equals AM sin 2 pi FMT. We are considering a sinusoidal modulating signal, correct. We are considering a MT, we are considering specifically to be a sinusoidal message signal. Okay. We are considering the specific case of a sinusoidal message signal with amplitude AM. This is, as you know, AM is the amplitude, FM is the frequency of the sinusoidal message signal. FM is the frequency of the sinusoidal message signal. Okay. And therefore, in this scenario, remember, in phase modulation the message signal modulates the phase of the carrier. Therefore, we have theta I t is basically 2 pi fct, that is the regular phase 2 pi fct, plus the phase offset which is given by the message, that is kp times mt. Therefore, we have theta I t equals 2 pi fct plus kp times mt, but we have mt is am sin 2 pi fmt. So, this is simply your 2 pi fct plus kp times an sin 2 pi fmt. So, this is your theta I t, and therefore, the net modulated message signal is given by St equals AC cosine theta I t, which is basically your AC cosine 2 pi fct plus kpam sin 2 pi fct. This is the modulated signal. Okay. St is your St is the modulated signal. Okay. Now, Fit, that is we have theta I t. Now, the frequency, instantaneous frequency Fit, remember Fit is your instantaneous frequency. Okay. So, this so the instantaneous frequency is given as 1 by 2 pi d theta I t by dt, which is basically given as, which is basically equal to this is equal to f c, well 1 over 2 pi, let us write the expression for d over dt of, well, theta I t, as we know 2 pi f c t plus k p a m sin 2 pi f m t, which is equal to, well, f c plus, well, the derivative 1 over 2 pi times the derivative of k p a m sin 2 pi f m t, which is k p a m into 2 pi f m into the derivative of sin 2 pi f m t is cosine 2 pi f m t, and now basically this can be simplified further as f c plus, we have the 2 pi's cancelling. So, this is k p a m f m k p a m f m into cosine pi f m t. This is the instantaneous frequency. This is your expression for the instantaneous frequency. This is the expression for the this FIT, this is the expression for the instantaneous frequency FIT of this phase modulated signal, phase which is modulated by the sinusoidal message signal AM sin 2 pi FMT. Okay. Now, this is FIT, let us find the frequency deviation of this. Remember, delta f, frequency deviation is the maximum of FIT minus FC, that is unmodulated frequency of the unmodulated carrier, which is basically maximum, as you can see from above. FIT minus FC is KP AM FM cosine 2 pi FMT, and therefore, the maximum of KP AM cosine 2 pi FMT, the maximum magnitude of this is basically Kp Am times Fm. So, we have delta f, that is the frequency deviation. Remember what is delta f? Delta s is the maximum frequency deviation. Okay. This is the maximum frequency deviation equals Kp Am times Fm, which implies that beta, now beta can be expressed as, therefore, beta can be expressed as delta f by f. Remember, beta is the modulation index of Fm, which is equal to Kp Am. From the above, it is Kp Am, well, delta f by Fm, Kp Am, well, let us write the complete thing, Kp Am Fm divided by Fm, which is equal to Kp times Am. Therefore, beta this is the modulation index equals Kp times Am. And look at this, you can see this Kp times Am, this is also equal to the maximum phase deviation. For instance, if you look at this thing, if you look at the phase, remember the phase is theta I t, theta I t equals, well, theta I t equals 2 pi f c t plus k p a m times sin 2 pi f m t. Now, phase deviation delta theta equals maximum magnitude delta I theta I t minus 2 pi f c t, which is equal to the maximum of, well, substituting theta I t minus 2 pi f c t, we get k p a m sin 2 pi f m t, which is equal to maximum of k p m sin 2 pi f m t is equal to k p m. So, this is equal to delta theta, and you can also see. So, this is delta theta, and this is also, you can see, this is also equal to your beta, that is the modulation index. So, for sinusoidal modulation, what you can see is beta equals, that is with phase modulation, with the sinusoidal modulating signal, with that is where the phase is given by 2 pi f c t plus k p times m t. What we have been able to show, that is for m t equals a m sin 2 pi f m t, what we have been able to show that this modulation index beta, which is defined as the peak frequency deviation divided by f m, the frequency of the modulating signal, that is equal to k p times a m, which is also seen to be the maximum phase deviation of the signal. Okay. So, we have beta equal to, what we have derived is, we have beta equals the modulation index equals k p times a m, which is also equal to delta theta, which is also basically, so your beta is basically the modulation index. And delta theta is basically the maximum phase deviation. And delta theta is a maximum phase deviation. All right. So, in this module we have seen an introduction. All right. We have started looking at angle modulation. We have said that there are two different kinds of angle modulation, namely phase modulation and frequency modulation. We have described an overview, we have given an overview of both phase modulation and frequency modulation, and we have also seen the specific case of a phase modulated signal for a sinusoidal modulating message signal. All right. So, we will stop here and continue with other aspects in the subsequent modules. Thank you.